So now we might believe that the consequences of quantum mechanics are essential for understanding the ordinary world around us. But is quantum mechanics actually useful? I mean, if we devote all of our time here to learning it, will it let us make things we could not make before? Well, one science in which quantum mechanics is obviously essential is chemistry, the science that enables most of our modern materials. And no one could deny that chemistry is useful. But supposing even we set chemistry and materials aside and ask a harder question, do we need quantum mechanics when we design devices, objects intended to perform some worthwhile function? After all, we seem to have been quite successful engineering all these devices of daily life, like washing machines and eyeglasses and staplers and cars, using basically good old-fashioned 19th century physics, even if we employ the latest alloys or plastics or paints or whatever to make them. Perhaps such macroscopic mechanisms can indeed be designed without quantum mechanics. However, when we want to look at the technology of how we communicate and process information, technology that is fundamentally transforming our professional lives and our social lives today, we have simply been forced to move to quantum mechanics. Without quantum mechanics and quantum theory as a practical technique, we simply would not be able to design the devices that run our computers and our internet connections. The mathematical ideas of computing and information had begun to take their modern shape starting in the 1930s and then in the 1940s and 1950s. And incidentally, that same John von Neumann that I mentioned sorted out much of the mathematics of quantum mechanics was also the person who came up with the basic architecture of modern computers. Anyway, by the 1950s, not only telephones and broadcast television were well established, the first primitive electronic computers had been demonstrated. Though the early technology of these devices was based on electromechanical switches and vacuum tubes, the transistor and the integrated circuit were the next key breakthroughs that allowed all this technology to scale up exponentially from then on. So here's a picture of a replica of the very first transistor. This was made in 1947, the original. And then later on into the 1960s, we started to have integrated circuits which could combine many, many transistors at once. And these, as I said, are the technologies that really allowed the exponential scaling of all the information that we handle today. They make complex computers and information switching and processing machines available for us. These are all what are called solid-state devices, these transistors, as opposed to vacuum tubes, which have got a lot of vacuum in them. And they rely very heavily on the quantum mechanical physics of crystalline materials. Now, it's true that a well-informed devil's advocate could still argue, though, that the design of transistors and integrated circuits themselves was initially still an activity using classical physics. Designers would use the idea of resistance from 19th century electricity, even if they added the ideas of charged electrons as particles carrying the current. And they would take the various electrical barriers or potentials that would persuade the electrons to go one way or another as being classical potentials, but in the end those really come from quantum mechanics. However, we could still say that that design is mostly sort of semi-classical. However, no modern transistor designer can ignore quantum mechanics. So here is a cross-sectional diagram, a rather simple one, of an actual transistor. In a transistor like this, current can flow between the source, which you see on the left, and the drain on the right, through the silicon substrate. And specifically, it can flow through that channel region near the surface of the substrate, near the top surface there. Now, applying a voltage to the gate electrode can change the number of charge carriers in the channel, and therefore change the amount of current that can flow between the source and the drain. This is the basis of the kinds of transistors we use in modern integrated circuits. There has, however, been a growing problem with the design of such transistors. As we want to make the transistor smaller, we find that we want to reduce the thickness of the very thin insulating gate oxide layer. That's a layer made probably mostly from silicon dioxide, or these days some other oxides are used. For example, we have to make this very thin as we go to small modern transistors. And the difficulty with that is that electrons can manage to penetrate through that insulator through a purely quantum mechanical process known as tunneling. There's no classical description of this. It's purely quantum mechanics. And as we design modern transistors, at the very least, we have to take that parasitic, undesired process into account. So here's the tunneling current going through the transistors, and it's because we are making that gate oxide thinner and thinner here. We're tunneling from the polysilicon gate electrode through to the channel, and we really don't want that to happen. Among other things, it gives us an undesired gate leakage current. So we simply can't anymore ignore quantum mechanics when we design the devices. Even if we think of them in kinds of semi-classical ways, the quantum mechanics comes in even if we don't want it to. Even then, if we set aside the properties of materials like silicon, from which transistors are made, we might argue, at least historically, about the importance of quantum mechanics in the design of the transistors themselves. We could think of them as being mostly classical devices, as I said, that turn off and on-and-off currents based on classical electrostatic effects, even if they have these undesired quantum phenomena like tunneling going on inside them. However, if we look at some other areas, we have no comparable debate. The technologies that we use for handling information in communicating it and storing it are undeniably quantum mechanical. We can't even begin to discuss magnetic storage or optical communications without that. And here is a typical little hard drive. We all have these in our computers. The physics of how we design and make and operate these hard drives is intensely quantum mechanical. The physics of magnetism is very quantum mechanical to start with, and the modern hard drives actually have got some very advanced quantum mechanics in them. And this here is an optical fiber. So I've got one here that has got a normal plug on the end that you would plug into something. But then as we go down towards the other end of this fiber, though it's a little small to see, we're seeing a green line here, but inside that green line is a very thin piece of glass. It's about the thickness of a human hair, and I can touch it up the end here. And that is what is used to send information over the internet. And it's very thin, as I said, and this reel of fiber here has 3.8 kilometers of fiber on it because it's so thin here, and you can see it's a kind of glassy thing. It's actually a reel containing all of that optical fiber. So when we are using these modern technologies, there's simply no way to understand how to design the devices for these without using quantum mechanics. In the case of the optical fiber, we're turning on and off these optoelectronic devices that send the ones and zeros as light pulses down the fiber, for example. And as I said earlier, those kinds of devices are ones that are intensely quantum mechanical. Now, with this reel of fiber here, we can understand how light propagates down the fiber without leaking out of the side by using classical wave theory. And that classical waveguide phenomenon that keeps the light within the glass as it goes down has been understood since the mid and late 19th century. And as I said, to send the light down here, we need these optoelectronic devices that send out photons. And all of those optoelectronic devices are quantum mechanical in at least one way and possibly many other ways. They are made from crystalline semiconductor materials, just like transistors, so they certainly certainly quantum mechanics underlies that as to how that all works. And secondly, as I said, they send and receive photons. They rely on the photoelectric effect for their basic operation. And thirdly, actually, most modern semiconductor optoelectronic devices, the ones that convert between electricity and light, the ones that are used in telecommunications, today employ very thin layers of material, layers called quantum wells. And the properties of these extremely thin layers, they're maybe tens of atoms thick, depend exquisitely on just how thick they actually are. And that is an example of a textbook piece of quantum mechanics, one of the simplest things we can model quantum mechanically, called the particle in a box problem. And that particular piece of quantum mechanics, optoelectronic device designers have to use every time they go to design a new laser or a new modulator or a new photodetector. They need that quantum mechanics. So this physics of quantum mechanics allows us to optimize some of the physical processes we already had in thicker layers of material, and also to create some new mechanisms that we're only going to see in thin layers. So for such devices, engineering using quantum mechanics is both essential and very useful. And as I said, when we try to pack more information onto our magnetic hard drives in a computer, we first have to understand exactly how the magnetism of materials work. And magnetism is almost entirely based on a quantum mechanical attribute called spin, and that phenomenon has no real classical analog. The sensors that read the information off the disk drives in our computers today are often also based on very sophisticated structures with multiple thin layers, and those are designed completely with quantum mechanics. Quantum mechanics is then a subject increasingly necessary for engineering devices, especially as we make them smaller and smaller, or as we exploit quantum mechanical properties and processes that only exist because we've made such small structures. And the examples I gave here are only a few from a very broad and growing field that could be called nanotechnology. Nanotechnology exploits our expanding abilities to make very small structures or patterns. And the benefits of nanotechnology come from the new properties that appear at these very small scales. We get most of these new properties from quantum mechanical effects of one kind or another. Quantum mechanics is therefore essential for nanotechnology.